Okay. Good afternoon, good morning, and probably good evening, everyone. Thank you for joining today's webinar with Dr. Ricardo Vinuesa. Before starting the talk, let me introduce the International Society for Computational Fluid Dynamics, ISCFD for short. The ISCFD is run by a dedicated team of like-minded volunteers, including myself, who aim to increase the visibility of CFD research. Our purpose is to bring people and ideas together by creating opportunities for knowledge and exchange, such as this webinar. We regularly host CFD professionals from varying backgrounds to share their work and perspectives. If you like the idea and format, we invite you to follow us on LinkedIn, Twitter, and recently our brand new official website for updates. Also, there are some past events on our YouTube channel, so please feel free to check them out. Today's event is expected to last about an hour with 45 minutes of talk itself and 15 minutes Q&A session. If you have a question, please post it in the chat. I'll collect them and read them out loud at the end of the talk. And now, today we have the chance to meet and listen to Dr. Ricardo Vinuesa, who is an associate professor at KTH in Sweden. Before becoming part of this institution, he received his PhD in mechanical and aerospace engineering from the Illinois Institute of Technology in Chicago. Currently, his research focuses on numerical simulation and data-driven methods to analyze and understand the complex structures in turbulent flows, such as boundary layers developing in winds, among others. Also, he's a researcher at the Artificial Intelligence Sustainability Center in Stockholm, which is going to be the focus of today's topic, and vice director of the KTH digitalization platform. And now, without further ado, Dr. Vinuesa, the floor is yours.
Thank you very much for the kind introduction. And let me share the screen. Please let me know if you can see the slides. And I will also make it screen. Can you see the slides?
Yep, everything looks perfect.
Great. Yes, so I will talk today about artificial intelligence, computational fluid dynamics, and sustainability. And as mentioned, I'm an associate professor at KTH, and I also work at the AI Sustainability Center. And this research is funded by SERC, the Swedish E-Science Research Center, but also by the Göran Gustafsson Foundation. So I will start with an introduction. I'm going to talk about two different things. First, I will talk about how to use AI for sustainability. And in the second part, I will focus on one concrete example of how this can be done. How can I use AI for sustainability, and what is the potential and the implications of this? So in this first part of the talk, essentially, we wanted to answer one question, and as the question is there any published evidence on how AI can help or it can hinder the achievement of the 17 Sustainable Development Goals of the United Nations, the famous SDGs. And these goals range from aspects related to climate change, but also it has the social aspects. There's social stability, political stability aspects. So there are many things that are included in these development goals. And because it's very diverse and it's a very wide range of areas to tackle, we needed to have a multidisciplinary team to be able to look at all these areas. So what we did was to consult with, we formed this very diverse team. So there are experts in fluid mechanics and AI, but also more applied AI in the social interaction aspect, theoretical AI, ethics. There's people, experts in biology, experts in energy and sustainability, and also legal and economical experts. So we could really look at this from quite a broad perspective. And all these results, you can find them in this paper that you see here. So it's Nature Communications from last year. And here I will just highlight some examples of how this connection between AI and the Sustainable Development Goals can be made, both in terms of positive effects and negative. So the first thing that we did was to split the 17 goals into three categories, the ones that have to do with society, with economy, and with the environment. So you can see here both the symbols and the statements connected to each of these goals, because we thought that it would be much easier to really understand the implications of all these SDGs if we divided them into these areas. And to look broadly at the results, these 17 SDGs that are divided into three categories, they include a total of 169 targets. So these targets are connected to the 17 SDGs. And if we look at all those targets, what we find is that 79% of the targets can be positively affected by AI, and only 35% can experience a negative effect because of the development of AI. And if we look at the three separate categories, what we see is that the environment has, in principle, the highest positive impact from AI, and the highest negative would be in the society. Now, one thing to keep in mind here is that we're looking at kind of like a big picture relations, but we're not taking into account the fact that even if the effect of AI is more positive than negative, in all the SDGs, it could be that one target negatively affected by AI could have really, really negative and catastrophic consequences. So one should not just think, okay, AI does more good than bad, then we're happy and we're good. One should also think of the possible negative consequences that can escalate, okay? And what we also did was to look in detail at each of the SDGs. So what you see here on the left is the total of the 17 SDGs with the percentage of targets from each of these goals that are positively affected by AI. And on the right, what you see is the percentage of targets that have a negative effect of AI. So the percentage of targets from each of these SDGs. And again, I mean, you see that there is a more positive than negative effect. Let's focus now on these lighter lines, not the black and dark ones, but the lighter ones. And we can see basically the implications in all of the three areas that I mentioned before. Now, we can do one more thing as well, right? Because here we're just looking at published evidence that shows positive or negative effects on each of the targets from the SDGs. However, not all the references are the same. And there are different types of evidence. So what we also did was to classify all the references, all the studies, all the research that we found, to classify it into 4 different categories. Going from the most robust and sophisticated studies, which were labeled as an A reference, going down to a D reference, which would be studies that are very speculative or not so easy to generalize, so perhaps the strength of that evidence was not so high. And then we gave weighting factors to each of these. So the A references have a weighting factor of 1, whereas the D references have a weighting factor of 0.25. So basically, a positive or a negative effect documented by a D type of evidence would be much weaker than an A type of evidence. So what we can do now is look at not the light, but the darker color, and the dark green and the dark orange here for the positive and negative effects. And we can see how these effects change when we take into account the strength of the evidence. So clearly the dark lines are going to be smaller or equal than the lighter ones, because the maximum weighting factor is 1. And we see 2 interesting phenomena. If we look at the environment and the society, so these 2 regions here, what we see is that the reduction, when taking into account the strength of the evidence, is very big in the negative effects. So the negative effects of AI in the environment and the society are not so well documented. They're a bit more speculative. However, when we look at the economy, the opposite happens. In the economy, the negative effects are quite well documented, but the positive effects are not so well documented. The positive effects of AI on the economy, there is so much potential and everybody is talking about it, but perhaps concrete evidence and concrete robust studies, that's certainly an area of research that needs to be developed. And I believe this is something important to keep as a conclusion of this. Sorry about this slide. Let's go to the next one. There we go. So what I'm going to do now is that I'm going to talk about the concrete examples. And again, you can go to this reference and see the very detailed discussions and all the examples that we have identified. Here, I will just give a bit of a highlight of the most relevant examples of these relations. So, and of course, this first part is a bit of an introduction. Later on, I will talk more about CFD because we are here to talk about CFD. But I think that this connection with AI, I think it can give a nice background to all the work that we can do within computational fluid dynamics. So the positive effects of AI, for example, in SDG 1, typically have to do with new technology that was not available before. For example, there is a very nice study by John and others where they have used satellite data to track poverty. So with this satellite data, they can really find concrete parameters that can help to track poverty and therefore help with the achievement of SDG 1. Negative effects. Well, AI is unlocking new technologies and new, it has really the potential to do things that were not possible before, but at the same time, it's associated with uneven opportunities if the access to AI is not uniformly distributed. And then we will have unequal access, which would increase the inequalities, and that, of course, will have negative effects on SDG 10. So potential of AI with new technology, but if not everybody can access this technology, then we will have even more inequalities and therefore we will be worse off. Some more examples, for example, clearly we live in challenging times, so there is a strong political polarization, bias, election outcomes, misinformation, and all of that is being triggered by the AI algorithms present in social media when sharing information and when trying to make things express opinions and show evidence and documentation of those opinions. Sometimes the AI algorithms in social media are biasing the information that we get, and that is polarizing the society. So as a conclusion, perhaps an important point is that, well, it's important to regulate AI, and there are now big initiatives in the European Union. UNESCO has their AI Act as well, but perhaps it's even more important, the regulatory insight. So basically to have people who are well, experts in the technology, technocrats, who are involved in the decision-making process and in the policy development process. So it's important to regulate, yes, but it's important to have the impact and the input from people that know about the technology and not limit ourselves to purely political decisions. So more things. I'd like to talk about another example of data-driven methods that have ethical implications and sustainability implications. In this case, for example, we can talk about the contact tracing apps for COVID-19, which were very, very widely discussed, especially last year. This, of course, has implications on SDGs 3 on health and 10 on inequalities. And we develop a series of guidelines. You can see this article in Results in Engineering, so you can find the details of this study here. And what we did was to basically see what are the ethical and technological requirements of these applications. And for example, we really recommend to use decentralized data gathering. So, for example, the DP3T protocol, which is excellent for this, was one of the recommendations that we had. And as you can see here, we actually had, we analyzed several apps with respect to their compliance with these requirements. And we found that the European Data Protection Board guidelines were not enough in many cases. So we actually provided more comprehensive guidelines to try to improve the development of these apps, which could have helped with COVID-19 strategies. And another thing that I think is important is to talk about the dynamics. So the dynamics of all these agents in the development of AI and data-driven technologies and the relation with sustainability. So we have here the technology, which of course is advancing very fast, which means that we have important new possibilities for the individuals, for the users, who have also new needs for technology. And what we can see in this cycle is that the government is very slow. I mean, the regulation, the standards and the policy, they're much slower than the interactions that come from the technology and from the individuals. In this figure here, the thickness of the arrows indicates the speed of change. So how quickly an agent is interacting with the others. And of course, there is a strong impact also on the environment. The environment is an underlying layer where we have exchange of resources, but also we have an impact, climate impact, which is another topic. So here, what we want basically is that we can reverse a little bit this cycle and that we can have faster policy development, but at the same time, adequate technocrat solutions for this development of policy. So this is, and here you can see that the thickness of the arrows was connected with the speed of change. So now going a bit more into the CFD part and why I tell you all of this, I think that one should exploit all the possibilities of technology to try to have a more sustainable future and to tackle all these goals. And one example that I like very much is SDG 11 on sustainable cities. Every year, 800,000 people die in Europe because of exposure to too high pollution levels. And we really saw in our study that AI can have a huge potential to achieve and to help tackle the challenges associated to SDG 11. So what do I propose to do? Well, one possibility is to use highly detailed simulations. And now we go more into the CFD. So we can use highly detailed simulations to characterize urban environments. And then we can go from sparse measurements in the city to reconstructed flow, three-dimensional reconstructed flow fields. And we can train deep learning methods, different types of models, with a highly detailed simulation data to go from these black dots, which are sparse measurements, to this three-dimensional flow field that you can see here. And of course, if we have a good idea of the three-dimensional flow field, we can also understand better the temperature, the pollution levels, and then have better strategies to tackle and to control the conditions in the city. So these are some of the methods that I propose to do what is called the non-intrusive sensing. Non-intrusive sensing means that we can sense, we can measure in the city, but without putting sensors in the city. So using sensors on the ground, on the walls, on the sides of the buildings, we can reconstruct the 3D volume in the city. And there are different ways using deep learning to do this. And here you can see the type of very detailed simulation data that we use. Here we have two obstacles with different separations, with different flow regimes, and we use these spectral element simulations to really understand in detail how this flow field looks like and how the deep learning models can be used to do these predictions. Now, these predictions in urban environments are complicated because these flows, as you can see, are very chaotic and you have a very wide range of scales. So what I will do is that I will consider a simpler flow case to start, and I will illustrate the potential of the considered methods to really perform these reconstructions and to see how accurate results we can really get from this. Okay, so this brings us to the second part of the talk, which means to do non-intrusive sensing, and to do that we will use convolutional neural networks. So I'll give you a bit of an introduction of this type of computational frameworks and the type of simulations that we do to try to understand the flow data in these cases. So to do this type of predictions from the wall information. So if you remember the slide with the building, we are measuring at the wall and we want to predict the three-dimensional flow. This has been done for many years using linear methods. The linear stochastic estimation is a very widely used method. And we have a study that you can see here in Journal of Fluid Mechanics, Saki and others, where we consider transfer functions in a spectral space to connect the input and the output. the input being the wall information and the output being the information above the wall. I can see that there are some questions, but I will answer all the questions at the end. And I see some very relevant questions, so this is really, really great. So, for example, with sensor density, we will talk about it in a few slides ahead. So what we also found is that using both linear and nonlinear transfer functions, we obtain different levels of performance. And the nonlinear transfer functions that we employed in this study gave us much better results. Why did we observe that? Well, turbulence, and I'm sure that many people here know about turbulence and turbulent flows, and there are two fundamental mechanisms by which you look at scale interaction. One of them is the superposition of the large scales on the small ones, and that's typically a linear phenomenon. But there is also a modulation effect, modulation of the amplitude and the frequencies, which is a non-linear effect. And of course, in this, if you're using models that are linear, then you are not able to reproduce the nonlinear interactions, whereas neural networks, and I will talk about them in a second, they can reproduce nonlinear relationships between the variables. Therefore, they are very well suited to make predictions in turbulent flows. So if we look at the example that we consider, we will look at an open channel flow. An open channel is basically a flow in which at the bottom we have a wall and at the top we have a symmetry condition. So it's a fully developed channel that is open. And we are doing a DNS, a direct numerical simulation. We use the Fourier Chebyshev code Simpson, developed at KTH. And the reason to use this open channel instead of a normal channel with two walls is that the large scales in a normal channel, they have effects on the two walls. A very large vortex is going to be sitting probably on the bottom wall, but it's going to affect the upper wall as well. And that complicates a little bit the dynamics. So it's slightly simpler to have just one wall and to make the predictions based on that. We have a low Reynolds number, friction Reynolds number of 180, and these are the parameters that we have. You can see all the information in this work by Guastoni and others, who is a PhD student in my group, and he has done many of the results that I'm going to be talking about today. And what we want to do is use different types of neural networks to perform these predictions. Remember that we will use wall information to predict the flow above the wall. Fully connected networks like the MLP, multi-layer perceptron, recurrent neural networks, they're very widely used, but they have one problem, and it's that each of the neurons from one layer is connected to all the neurons of the next layers, which means that very quickly the number of parameters increases exponentially. And especially if you're using images and very large databases, these networks are not very practical. And they're prone to overfit the data because you have so many parameters that it's actually very difficult to train this type of models. However, there's another type of network, which is what is called the convolutional neural network, and you can see an example here, which is very widely used in computer vision, and it works as follows. You have your input field here. Now you have a little window, a kernel or a filter, and this window is sweeping the input data, and the output, in this case, this -8, is one value that receives information from these 9 points over here. And I will explain a little bit more about how it works. This is a convolution operation. The nice thing is that the number of parameters is much lower. It's just a little window with a certain sweeping through the input, and therefore with much fewer parameters, we can actually treat images in a very efficient way. And this is what we're going to do. We want to use information at the wall. So this is the blue surface that you see here. For example, in this case, we show results from the two wall shear stress components. And using a convolutional neural network, we're going to predict the fluctuations at a plane that is above the wall. So this is this yellow plane that you see here. In this case, we're going to predict the streamwise velocity fluctuations on that plane based on information that we measure here, which is at the wall. Okay, and one more motivation of this would be for closed-loop reactive control. I mean, closed-loop reactive control is based on applying a certain actuation at the wall based on the flow above the wall. And if you can have a very good mapping between what happens at the wall and what happens above, then we can design better control strategies. Okay, so we use this off-wall to do this off-wall prediction tasks. We use convolutional neural networks. This is the CNN, the convolutional neural network architecture, and as you can see, we have an input with two planes, because we have the two Walsh stress components. We have an output here with only one plane, which is the stringwise velocity fluctuations, and we have a total of 6 hidden layers in between. And these are the different layers that we see here, with a number of feature maps that we are going to be talking about in a second. So in the input layer, we will have 128 square grid points. So each of these planes has 128 square, and we have 2 planes. That's the same size of the output layer. Here, I will not discuss in detail the periodic padding, but because the fields are periodic, there are some things with the periodic padding that need to be done here. And we have a total of 6 hidden layers with a ReLU, the rectified linear unit activation function. Okay, and this type of activation function is very widely used in computer vision, and it works pretty well. These numbers here are the depth of each of these feature maps, and is the number of stack layers after each of the hidden layers that we are considering in our network. Okay, so to explain that a bit better, let's consider the first filter. This is the first hidden layer, okay, with the first filter, and this has a total of 64 features, so 64 stacked feature maps, and this filter has a size of 2 times 5 times 5. 2 because that's the depth of the input, and we have 2 planes here, and 5 times 5 is the size of that kernel. That little window that I showed before in the first layer is going to be 5 times 5, so that's 25 parameters, and that means that I have a total in this first hidden layer of 50 parameters. 5 times 5 times 2. If I had a fully connected network instead of a convolutional network, what I will have is a total of almost 33,000 parameters. So you can see here why it is so interesting to use convolutional networks for images, because images is a bunch of pixels, 128 square, as I mentioned before, which means that if we use fully connected networks, we're going to have so many parameters to adjust, and that's going to be very expensive to train. Convolutional networks with only 50 parameters, we already can perform very good predictions, and we can already have very good identification of the features in that input. When we go to the application of this first kernel, what we have is that each filter identifies a different feature on the flow. So this filter is going to be applied a total of 64 times, and we're going to obtain 64 feature maps on this first layer that we see here. Now, the next filter is going to have a depth of 64, because we are applying a convolution on an input that now has a depth of 64, and the little kernel, the little window, is going to be a bit smaller. Instead of 5 times 5, it's going to be now 3 times 3. So we have 576 parameters, still significantly less than we will have in a fully connected network, and we apply a total of 128 filters. So again, we get all these features, and one thing that you can start to realize, I mean, the features that we see here, the features that we talk about in turbulence, they can be, they're usually structures, okay? They can be streaks, they can be regions of high fluctuation, they can be regions of recirculation and backflow. So they are structural features in the flow. And what you can see from the definition of the convolution, as I showed before, is that as I go deeper into the network, that the result of that point is obtaining information from more and more and more data from the input. Because as I go deeper, progressively larger features have been identified. Or to put it differently, the outputs are based on more and more grid points from the input. So the first layers identify small features, the last layers identify large features. Okay, and this is important because, as you know, turbulence is a multi-scale phenomenon, and therefore this multiplicity of scales is important in our architecture. Okay, so types of convolutional neural networks. As we can see here, we can have at the end, I mean, I have many convolutions, and at the end, I can have 2 types of output. One type is when I have just a a global output, which means that at the end I'm going to connect. I'm going to have a fully connected network or several connected networks at the end. And this means that my output is going to be, for example, a classification task. I have this image and my output is just one label or one number, in this case, car. Okay, this is a car. That's obtained by adding fully connected layers at the end. If I have fully convolutional networks all the way, so I don't have a connected layer at the end, but I just have fully convolutional layers all the way, my output is not going to be a scalar or a label. It's going to be another image. So in this case, what I have is a city image, and that's my input, and my output is a classification input, it's a classification task with local outputs. So this region is the pedestrian cross, this is the road, these are the cars. So you see, by adding a connected layer at the end, what I have is a global output, but if I keep the convolutions in all the layers, I keep a local output. So each region of the original image gets its own output in terms of the classification that we have. Okay. So this is, let me see if I can go to the next slide. Very good. So let me show how to apply these convolutional networks to the example that I showed of the open channel. What I'm doing is that I'm using information at the wall. Remember the two wall shear stress components, and I'm predicting these fluctuations above the wall. Here I'm looking at y plus 15. For the ones that know about turbulence, you know perfectly that this is the near wall peak. For the ones that they are not so familiar with these quantities, just to give you the information that this is a region with very strong fluctuations, close to the wall and very strong fluctuations. And this is the reference. As you can see, turbulence is characterized by extractors, as I mentioned before, these features that are being identified by the network. And you can see here that these are streaky extractors, and these elongated patterns are near wall extractors. And the key is whether my network is going to be able to identify or not these extractors in the flow. And this is the reference. This is what we want to predict. On the top, we have the result from the linear method, linear stochastic estimation, and on the bottom from the neural network. And what we can see is, first of all, the LSE, the linear method, is very attenuated. And second of all, it doesn't have all this wiggliness that these streaks have. And the reason is that the wiggliness, this kind of meandering, that's associated to nonlinear effects that are being superimposed in those streaks in the near wall region. And the neural network, which is, as I mentioned, a nonlinear method, can model and can predict these nonlinearities. Therefore, we get much better results with the neural network. If I go farther away from the wall, to y plus 30, as we can see here, well, the neural network is still predicting pretty well the results, and the linear method is saturated. We cannot really predict the amplitude of these fluctuations. And if I go even farther away, the linear method doesn't show very much, and the neural network starts to exhibit some deviations. It still captures the extractors quite well, but some of the details of the extractors are not so well reproduced. This can also be well, it can be alleviated if we look at the time step between samples. When you're farther away from the wall, the extractors are larger and the time scale is slower. They move more slowly. So it may be that sampling with a higher spacing between samples gives better results. And that's what we observe here. By increasing the spacing between samples by a factor of 3 more or less, we can see a much better agreement with reference data. And all of this can be found in this paper by Wastoni and others in the Journal of Physics conference series, okay, 2020. We can also see, if we look at the turbulence statistics, on the left we show the mean flow, on the right we show the near wall, well, the stream velocity fluctuations with emphasis on the near wall peak. And what we can see is that the orange and blue are the neural network results based on different time steps, and the green ones are the linear method. Just to give you an idea, in the near wall peak, we have less than 3% error with the neural network, and the linear method has 12% error. And far away from the wall, we get less than 30% error with the neural network and 44% with the linear method. Now, these results can be improved even more when we look at extending this data to a higher Reynolds number. Now we're going to look at a friction Reynolds number at a tau of 550. and we're going to complicate a little bit the predictions. We're going to use 3 input fields, so the 2 wall shear stress component plus the pressure, and we're going to predict the 3 velocity fluctuations, the string-wise, wall normal, and span-wise velocity fluctuations at different wall normal locations. Now, all these results, you can find them in this other article, also from Guastoni and others. You can see it in archive, and all the details are provided here. So you can really check all the details of the implementations of basically how to perform these predictions. We also consider another method. So far, what we have been doing is having my input, which is basically an image at the wall, and apply the convolutional network to predict the output, which is another image at a certain wall normal location. However, it's possible to use POD. POD is proper orthogonal decomposition. And this is illustrated here. When we do a POD, what we do is that we decompose our signal into spatial modes and temporal coefficients. So we separate the time and the space. And those spatial modes are fixed. So the only thing that we need to predict is the temporal coefficients. And the advantage of this method is that we are encapsulating part of the information into those spatial modes. So it is possible that we can get better predictions using this. We're going to call this method FCN-POD because it combines the fully convolutional network and the POD approach. And I will tell you in a second how it performs, okay, compared to the other method. So what I'm showing here is 2 wall normal locations. The first column is y plus 15. Remember, this is the near wall peak. The second one is y plus 100, so that's farther away from the wall. And I'm showing the string-wise velocity fluctuations for different methods. The third row, this one, that's the DNS, so that's the reference, that's the true data. You can see that this is Arita 550, so the scales are smaller in outer scaling. The bottom row is the FCN, the fully convolutional network, and the second row is the one that combines convolutional networks and POD. Okay, and the first row over here, we call it extended POD, which is basically like the linear method of before, like the linear stochastic estimation. Okay, so the first row is the linear method, the second one is the one with the POD, and the final one is the one with just the neural network. And what we can see is that close to the wall, the FCN method, just the convolutional network, is in excellent agreement with reference. And when we go farther away from the wall, is the one with the POD that is a bit better. It's a bit better than just the FCN. And the linear method, well, I mean, it doesn't perform very well. We can see that it's very attenuated, the nonlinear effects are not very well captured, and the details of the streaks are also not very well reproduced. If we look at the statistics, in this case, we don't only show the string-wise fluctuations, but also the wall normal and the span-wise. Well, what we see is that we can reproduce close to the wall, the near wall peak of the string-wise velocity fluctuations, we can get it with less than 1% error, which to me is actually very, very good performance with the FCN method. And what you can see, the orange triangles are the FCN and the blue circles are the FCN-POD. What you can see is that when we go far away from the wall, the POD method performs a bit better. Okay, and the linear one is always underperforming compared to the others. So why does the FCN-POD perform so well far away from the wall? That's because the large scales, in principle, they can be encapsulated, the information of the large scales can be encapsulated more efficiently into a bunch of POD modes. And when I only need to predict the temporal coefficients, well, that's an easier prediction than having to predict the whole extractor. Close to the wall, because the extractors are smaller, but also more energetic, it's not so easy to encapsulate that information into a few POD modes, and that's why the FCN method works better. But for the larger scales, in a way, the FCN-POD performs better because of the way that the information is stored into those spatial modes of the POD. Okay, and again, all the details of this can be found in this working archive. So feel free to email me if you have any questions or you want to see some more detailed explanations of these results. Now, this is one of my favorite parts because I really see a lot of potential in machine learning and deep learning in this area. So this is what we call the transfer learning. Okay. So what is a transfer learning? Transfer learning is basically when we train a certain model to do a certain task, and then we transfer part of the information learned for that task to another model for another task. Okay, and we have two examples. The first example is documented here again in the Journal of Physics conference series. We train a network to do predictions at y plus 15, so that's close to the wall. And then we want to do predictions at y plus 50. So the information close to the wall, I want to use it farther away from the wall. What I do is that the three first layers get frozen. So I use the same ones for 50 that I use for 15. And the three last networks, I train them. Okay, so those ones I start from the value that I had at 15 and I train them again. And these are the results. What I see is that with the transfer learning, I obtain very similar results in terms of mean and fluctuation errors, but at 1/4 of the computational time. The training time is reduced by a factor of 4 because of the transfer learning that I did. And one explanation for this is that, as I mentioned before, the first layers are in a way reacting or identifying features that are smaller, and the final layers are looking at features that are larger. And of course, close to the wall, the things are smaller, and as I go farther away from the wall, the small scales are more or less similar, or the small scale features, whereas the large scale features are changing as I move farther away from the wall. So freezing these first layers and changing the final ones is a good approach. That really helps to reduce significantly by a factor of 4 the training time. And this is another very cool example. So this one you can see in the archive paper. So what we do is that we train a network to do predictions at Arita 180. I'm showing you the example of y plus 30. And then I take the same model to do predictions at 550. And I do the training to do the predictions at 550, but I initialize the training from the weights at 180. Okay. And what I can see with these results, basically what I do is that I start to reduce the amount of training data. What we can see is that we can obtain exactly the same results at the high Reynolds number with 25% of the training data. What does that mean? Well, that has very important implications because, of course, the simulation at 550 is orders of magnitude more expensive than the simulation at 180. So this means that instead of developing a model where I need to run, let's say, I don't know, 10,000 instantaneous snapshots at 550, which is very expensive, what I can do is that I can get 10,000 snapshots at 180, which is very, very, very cheap, and then use only 1/4, 2,500 at the high Reynolds number that is much more expensive. So this is transfer learning allows us to exploit the similarities of the physical phenomena in different cases, but by saving a lot of computer data to produce training databases, training data sets, we can obtain similar performance with a much more efficient usage of the computational resources that we have. So this actually has a very important potential, connecting with the sustainability aspects of before. If we can reduce the consumption and electricity usage of these models, then we are really doing the environment a favor, but also from the perspective of the time that it takes us to develop a model, this is much more efficient. So transfer learning is very important to be able to exploit what has been learned in one task and apply that to a different task. This is very, very important. And then this is another recently accepted study. Okay, this is something that connects with one of the questions that I saw before, which had to do with the density of the sensors, right? I mean, how are you measuring? Well, what I have shown you so far assumes that I know everything at the wall, okay? So I have all the information at the wall and I'm predicting the flow above the wall. However, in reality, we don't have all the information at the wall. We just have a bunch of measurements. So what we did was to, here on the bottom, I'm showing you a little bit an schematic of what we do, is that we take the original field. This is the wall shear stress, instantaneous wall shear stress field, okay, at the wall, and I downsample it. So I reduce the resolution of this by a factor of 4 in its direction, by a factor of 8 in its direction, and by a factor of 16 in its direction, okay? What does that mean? That means that modeling the fact that I don't know all the information at the wall, I only know, some points that are distributed here and there. And you can see that this input barely looks like this one. It's very, very different. But we can actually obtain, on the bottom row, you see the predictions, we can actually obtain very, very good predictions of the input data that we have before. So what am I doing for this method, for this type of prediction? You can see all the details in this article that we just published. Okay, this is Güemes and others. A collaboration with my friends from Carlos III in Madrid, and this is accepted now. It's published now in Physics of Fluids, so you can really see all the details there. We use what is called the generative adversarial network, GANS, and this is a very popular architecture used for super resolution applications. And how does this work? Well, essentially, this is an example from Kim and others. I have a low resolution image, and this network has two parts, the generator and the discriminator. The generator, it needs to create images, in this case in high resolution, with the same statistical properties as the reference ones. Okay, so it's generating a new data set of images, fulfilling the same statistical properties. And of course, these high resolution images, they are not true, and they are fake, they are made up by the generator. And the discriminator, which is the second part of the network, its job is to differentiate which ones are the original high-resolution images and which ones are the fake ones produced by the generator. And this network is trained using game theory. So basically, the generator gets progressively better at producing fake images, and the discriminator gets progressively better at identifying which ones are fake and which ones are not fake. That's kind of like the layman explanation of this type of network. And what you can see here is the whole process. We have two steps. In the first step, we take the three quantities at the wall, the stringwise and spanwise wall shear stresses and the pressure at the wall. You can see that these have low resolution. These are very, very costly resolved. Through the first step of the GANS, we obtain high resolution images at the wall. And the second step is to use these high resolution images at the wall to predict the high resolution fluctuations above the wall. Okay, so what we have been doing so far before was to use wall information to predict fluctuations above the wall. Now what we do is that we take wall information with coarse resolution, we improve the resolution at the wall, and then we predict the fluctuations above the wall. Okay, and what I'm showing here is the information at the wall. So I'm showing you the super resolution task, and you can see, I mean, with low down samplings, the agreement with the reference is excellent, and so this is very good. But even with this very, very, very coarse input, what you can see is that the extractors, they are very well reproduced. I mean, we get some attenuation of the fluctuation intensities. Some of the details of the streaks and the wiggling of the streaks is not so well reproduced, but the size and the locations of the extractors, of these streaks, they're very well reproduced from an input that, as you can see, you cannot see anything here, right? So it's quite, to me, it's quite impressive that from this very coarse image, you can actually get something like this, which looks very physical and quite okay. Okay, and this is a wish list of future applications. We have shown that we can use neural networks to predict turbulent flows, basically. There are some other applications, the development of boundary conditions, of inflow conditions, tracking of turbulence extractors, non-intrusive sensing, flow control, and also an area where we are working a lot. We have a couple of articles that we are planning to release quite soon on nonlinear model decompositions and model reduction based on autoencoders. And this is a very, very cool area as well. So this is a little bit some of the future directions that we are working on. We're also working on physics-informed neural networks, PINs, which are another tool with a lot of potential. And I'd like to summarize a little bit my results. I talked first about the potential of AI with the Sustainable Development Goals, with quite some positive promise, and the capacity of CNNs, of convolutional networks, to perform linear predictions in turbulent channels. We can get the near wall peak with less than 1% error, which is fantastic, and we get much better predictions than linear reconstruction methods. So we are now working on other areas, more complex architectures, transfer learning, and we are looking at other possible directions of improvement of this work. And I'm very happy to, for this presentation, I would like to thank you very much for your attention. You have all my contact information here. This is my email, my research group web, and my Twitter account. So you can, if you have a question or you want to discuss more, you can use these means to contact me. And I'm very happy to take your questions. So thank you very much.